In the previous video, linked in the description below, it was shown that four disparate properties showing a flow across a gradient were actually related to each other through kinetics. One of these was electrical conductivity, which leads to the present topic of electrochemistry. Electrochemistry is the most relatable of everyday life of chemistry topics because everybody has used something that runs on a battery. So to start with, the transport property that controls electrochemistry is Ohm's law. Your flux dq dt is equal to the current, measured in amperes I, is equal to minus some conductivity, kappa, times the cross-section of the wire or the pipe across a voltage drop, a gradient of potential with distance. This can be rewritten such that, including resistivity, you have the change in potential is equal to a current times the length of the wire times the resistivity over the cross-sectional area of the wire, or the familiar Ohm's law, V equals IR, where a voltage is a joule per coulomb, and an amperage is a rate of a coulomb per second. For starters, look at the voltage. A voltage is a potential energy. Joules per coulomb is a potential for a charge to perform work. As a potential energy, it's an arbitrary point. You're above or below any point you pick. For electrochemistry, the 0 point is chosen to be the reduction potential of the hydrogen, where 2H plus 2 electrons go to H2 gas, being set at a reduction potential of 0 volts. This simply means that everything else is either above or below hydrogen. You'll also notice, once again, you have the superscripted 0 indicated that this is taken at a standard state of 20 degrees C, all gases at 1 atmosphere, and all solutions at 1 molar. Previously, in the study of thermodynamics, we saw Gibbs and his free energy, which was taken from the point of view of the system, where work enters or leaves the system, or heat enters or leaves the system. Therefore, the standard Gibbs free energy is negative for a spontaneous process, recalling that the standard Gibbs free energy is minus the integral of SdT plus VdP. On the other hand, Michael Faraday was a contemporary of Gibbs. They did not know each other well, and they did not know what they were working on, so he just took things from a different point of view. Instead of looking from the system, Faraday looked from the outside in. He viewed things from the point of view of his surroundings. That's the reason why a standard voltage being positive is spontaneous. You don't buy a minus 9-volt battery, you buy a plus 9-volt battery. The standard voltage, by the way, for any given battery is the oxidation potential plus the reduction potential, where for any individual half-cell reaction, the oxidation potential is simply negative of the reduction potential. So the Gibbs energy and the voltage are related to each other, except opposite in sign. The relationship can be determined by simply looking at the units. The Gibbs free energy is an energy measured in joules. The potential is a voltage measured in joules per coulomb. So essentially, the Gibbs free energy is going to be equal to minus the total charge Q times the voltage, or minus N, the number of moles of electrons, times F, which is Faraday's constant, times the potential. Faraday's constant has a value of 96,485 coulombs per mole of electrons. So, what happens in a standard state? the relationship still holds true. A statement of the second law is that the non-standard Gibbs free energy is equal to the standard Gibbs free energy plus RT log of Q. Substituting minus NFE for G, you wind up with E, the non-standard voltage, is equal to the standard potential minus RT over NF log of Q. This is called the Nernst Equation, which you may have remembered from your general chemistry. As previously mentioned, electrochemistry is interesting because it's something that you live with every day. Notice that the potential at any given non-standard state is equal to or proportional to minus RT over NF log of Q, where Q is your reaction quotient, products over reactants. So as you're aware, at any given time in a reaction, the amount of products will go up, so the value of Q will go up. However, if the value of Q goes up, the value of the voltage goes down. Essentially, this is why batteries weaken before they die. The reaction moves forward, you have more product, less reactant, the value of Q gets larger, the voltage drops before the battery completely dies. A battery is simply a series of galvanic cells. At the most basic, a galvanic cell can be made with two beakers. One beaker would have a zinc strip in it as the anode. The other beaker would have a copper strip in it as the cathode. Both beakers would be filled with a homonuclear electrolyte solution. An electrolyte solution being a salt solution, homonuclear meaning the zinc strip will have a zinc salt in the solution, and the copper strip will have a copper salt in solution. Oxidation occurs at the anode, so zinc will go to zinc 2 plus 2 electrons. Reduction occurs at the cathode, so copper 2 will receive those 2 electrons and be reduced to copper. Both of these half reactions have positive potentials. With the zinc reaction at plus 0.76 volts, the reduction at 0.35, one winds up with a total voltage of plus 1.10 volts. Since the voltage is positive, that means the reaction is spontaneous. Meaning, if I connect the two strips together, electrons will start to flow from the zinc to the copper, and as they're flowing, they can perform work. In this case, they will be lighting a light bulb. However, we have not made a battery yet, because one other thing is happening. If you look at the half reactions, in addition to 2 electrons, an extra zinc 2 plus is produced at the anode for every pair of electrons that are produced. At the cathode, when 2 electrons are absorbed, you lose a copper 2 plus ion from solution. So you now have an imbalanced state where I have more positive ions in the anode solution and more negative ions in the cathode solution. So every battery needs what's known as the salt bridge. The purpose of the salt bridge is to maintain electroneutrality. Positive ions will be sent to the cathode, negative ions will be sent to the anode to balance out the charges in solution so that once again, electrons can start to flow and work can be done. Again, this can be seen in everyday life if you've ever opened up an old flashlight and seen the battery had quote-unquote exploded. The caustic stuff that is all over the flashlight is the salt from the salt bridge. Another practical point with batteries for everyday life. Always, oxidation occurs at the anode, and the anode always receives the black wire when hooking up a battery. Reduction occurs at the cathode, which always receives the red wire. As mentioned previously, electrochemistry looks at things from inside the system. So, since electrons are leaving the anode, that is negative, and since they're going to the cathode, That is positive because a positive will attract a negative. However, in everyday life, from an engineering point of view, if you ever look at a car battery or any other battery, they use Faraday's convention to look at it from the outside. So the anode will always be marked with a positive on a car battery or any other battery. The cathode is a negative. The key thing to look for is how the wires are hooked up. That never changes. For any electrical or electrochemical system, the current or the rate of flow depends upon how quickly charge can transmit the distance. That is measured by resistance and or conductivity. They are inversely proportional to each other, and which one is used is essentially a matter of convenience. Resistance is generally used for metallic wires. It's an extensive property where the resistance depends upon the length of the wire divided by the conductivity of the metal, which is an intrinsic property, by the cross-section of the wire. So you see that the resistance is proportional to the length. Longer wires have higher resistance, inversely proportional to the cross-section. Thicker wires have less resistance. And resistance is used for metal wires, once again, because you wind up with a small, convenient number. The unit of resistance is the ohm, with the Greek symbol omega. In SI units, that's a kilogram meter squared per second cubed amp squared. Conductivity is also an extensive property and is generally used to measure how quickly ions move from solution. Conductivity, symbolized by the capital Greek lambda, is the conductance of that particular salt divided by its concentration in a given solution, where C is the concentration. Since conductivity is the inverse of resistance, it is measured in reciprocal ohms, 1 over an ohm, or Siemens. And generally speaking, lambda 0 is going to be the highest conductivity of a solution, the conductivity at infinite dilution, where you theoretically have one ion moving through the solvent. The study of conductivity has been central to physical chemistry. Arrhenius, whose name has been all over the place, actually got his thesis on the study of electrolytes, and it took him quite a while. What he was studying was what is called the degree of dissociation. Lambda of any given solution divided by lambda 0 at infinite dilution gives you alpha, the degree of dissociation. Theoretically, at the time, it was thought things either dissolved or didn't dissolve. Therefore, that number should always be 1, since it's a ratio. What Arrhenius found out was that it wasn't always 1. If you have what he called a strong electrolyte, an acid-base salt that completely dissociated, you would get a degree of dissociation of 1. However, if you had a weak electrolyte, which existed in equilibrium, your degree of dissociation would be less than 1. At that point, nobody actually believed that solutes could exist in equilibrium. So it took Arrhenius quite a while to convince everybody. In general, he finally showed that if I have any given weak acid, HA in equilibrium with H plus and A minus, that will have an equilibrium constant, the acid dissociation constant, products over reactants. And if I start out under a condition where I have initially some concentration of HA and no product, that will change, as in the product will go down by some percentage alpha times the initial concentration, and H plus and A minus will both go up by alpha C. So at the end of the day, your product would be the original concentration minus alpha C, and the two products, H plus and A minus, would simply be alpha C. So you get Ka is alpha C times alpha C divided by C minus alpha C. Or for any weak acid, Ka is the degree of dissociation squared times the original concentration over 1 minus the degree of dissociation. This was the basis of Arrhenius' thesis, and it took him several years to convince his committee that he was right. But he indeed was right, and basically revolutionized the way people looked at solutions and the properties of matter. Now, looking at ionic conductivity in more detail. When you have a salt, it is quite different than an electron moving along a wire. For starters, both species are going to be charged. If I have NaCl, I will get an Na plus and a Cl minus. So the total conductivity is going to be the conductivity of the positive ion plus the conductivity of the negative ion. Their mobilities are going to differ for a very simple reason. Anions are always much larger than cations. Specifically, chloride ion is 167 picometers, sodium ion is only 116. Therefore, the sodium ion can move much more quickly through the solution than the chloride ion can. This is quantified by the mobility, where for any individual plus or minus charge, the conductivity of that ion will be its mobility times Faraday's constant times that ion's concentration. At infinite dilution, that mobility is going to be the oxidation number times E, which is the fundamental charge, which can be found out by simply dividing Faraday's constant by Avogadro's number, and you get 1.602 times 10 to the minus 19th coulombs. So when you have an ion that's plus 1 plus 2, that's plus 1 or plus 2 times this fundamental charge, divided by, once again, the same as diffusion. How fast the ion is going to move depends upon the viscosity of the solvent and the size of the ion itself. So it's the oxidation number times the charge over 6 pi, the viscosity of the solvent, and the size, the ionic radius of the ion in question. Again, it's important to point out that not all ions have an oxidation charge of plus 1, and not all salts are going to be in a 1-to-1 ratio. This complicates the calculation of conductivity. What you wind up using is something called a transport number. The transport number tells you what fraction of charge each individual ion carries. Essentially, if you look at the positive charge, the transport number would be the conductivity of the positive ion divided by the total conductivity. Or put another way, the mobility of the positive ion divided by the mobility of the positive ion plus the negative ion, given the fact that Faraday's constant is constant throughout. To further complicate things, in real solutions, since I have positive ions with negative ions, and I cannot separate them, the activity becomes a mix of both. The activity coefficient, gamma, becomes a gamma plus minus for that entire salt. As mentioned, gamma plus minus theoretically is the activity coefficient of the cation plus times the activity coefficient of the anion, square root of that. Neither one of those can generally be known directly, so the term is inseparable. It can be found as follows. The base 10 log of this combined activity coefficient is going to be minus the oxidation number of the cation times the absolute value of the oxidation number of the anion. I to the half where I is the ionic strength, simply 1/2 the sum of, for each ion, the concentration of that ion times its oxidation number squared. And B is a solvent constant. That solvent constant can be looked up, but to be found, it is 1 over the natural base E, 2.718, times 2 pi Avogadro's number, the molar mass of the solvent, divided by the volume, to the half power, fundamental charge squared divided by 4 pi, the two terms. Epsilon is the dielectric constant of the solvent. Epsilon 0 is the dielectric constant of a vacuum. That's the standard. Times Boltzmann's constant times the temperature. Solvent effects are actually quite important in solution. Generally speaking, if you have an ionic compound with a cation and an anion, opposites attract. That's quite a strong bond. If something dissolves, that means when you put it into a solution, the attraction between the solvent and each individual ion is stronger than the attraction of the ions to each other. So the bond breaks and the ions are dissociated. There is now a weak bond between solvent molecules and the ions themselves. This is what's known as the ionic cloud. This surrounds each ion in solution. After Arrhenius, a German fellow named Karl Rosch was the first one to look into this. He essentially determined that the difference in conductivity between an ideally dilute solution and a given solution is some constant, his own constant, times the square root of the concentration. Debye and Huckel looked very much into this and found out that the constant in Karl Rosch's law was pretty much simply proportional to the temperature. There was an A value of the oxidation number squared divided by the viscosity of the solvent times the square root of temperature. The B value is the oxidation number cubed divided by the temperature to 3/2. The ionic cloud is actually very important from a practical point of view. The size of the cloud can be determined. The radius of the ionic cloud about the ion is the permittivity of a vacuum, the dielectric constant of the medium, Boltzmann's constant times the temperature, divided by the fundamental charge squared, the ion strength, as seen previously, times Avogadro's number to the 1/2. This goes back to how batteries work. If you recall, there is a salt bridge that is used to maintain electroneutrality. Theoretically, or in fact, the anode is always producing positive ions. This would stop the battery, except the salt bridge is balancing that out by sending negative ions across a membrane. This limits the rate of discharge of a battery. Current can't flow unless the charge in the solution is balanced. And in actuality, what happens is that the anions in the salt bridge are surrounded by an ionic cloud. This slows their progress to the membrane and also sets up something else called a double layer. This happens when there's essentially a log jam at the membrane and nothing else can get through. This double layer will stop a reaction until it clears, and it's only cleared when two ions manage to go through to make room for two more anions. Okay. This is a level of engineering that is actually vital to electric vehicles. The minimizing of the double layer and the increasing of conductivity through solution, minimizing the ionic cloud, is essential to basically have a battery that has high power output while giving off less heat. I hope you found this video interesting and useful. And next time we will be looking at surface chemistry linked in the description below. Thank you for listening. Take care.